Hello and welcome to this tutorial where I'll show you how to simulate a simple robot in ROS. My name is Nam and I'm a mentor for RoboSoccer this year. And I designed this tutorial mainly with beginners in mind. I wanted to show you an example of how you can create your own robot and how you can write a simple program to control it. So the goal for today is one, I will be covering a little bit of background about ROS. Yeah, I'll just go into like what ROS is, why we use ROS, etc. And two, I will talk about URDF files, which are a way to describe your robot in simulation. And then we will jump into some code where I'll walk you through what the code looks like, how you can change the code to sort of make your robot, and how you can write your own nodes to control the given robot. And finally, I'll leave you with an exercise where you can play around with the code and try to make your own robot, basically. Okay. So starting with ROS. ROS stands for Robot Operating System. And in essence, it's these four things. It is plumbing, tools, capabilities, and ecosystem. So it is plumbing because it sort of tells you how you're supposed to organize your code. It tells you how these running programs have to communicate with each other, how you're supposed to organize them, and so on. So it gives you sort of this framework of how you design your code when you're writing, say, C++ programs or Python programs, and so on. There's sort of a way that you have to write your programs to make it ROS. Tools. ROS gives you a bunch of useful tools. For example, you can have some visualization tools to graph your data, or maybe to visualize how your robot is oriented in the world. You can visualize what the robot is seeing or what it's thinking, and so on. It comes with simulations. So, for example, Gazebo is like the official simulator that comes prepackaged with ROS. Yeah, capabilities. ROS comes with a lot of libraries that have been written by other people. Libraries for, say, computer vision, path planning, localization. So it's a lot of libraries that you don't have to write. You can just basically borrow. So it saves you a lot of time when you're designing a robot. Instead of writing your own code, you can just borrow it from someone else. And finally, ecosystem. Ecosystem refers to the fact that ROS is such a widely used tool. It's used around the world, in like America, Europe, Asia. A lot of people use it, and so a lot of people contribute back to this tool. And as people contribute to the tool, you benefit from it. Everyone benefits from it. You can ask questions. You can borrow code from people. So if you use ROS, then that means you're interacting with this whole community of people. So as with anything, ROS will have advantages and some disadvantages. So I'll start off with advantages. So this basically sort of mirrors as to what I described in previous slides. So ROS has a bunch of useful tools like simulator, visualization tools. It is open source, so you can freely look at the source code. You can modify it. You can do whatever you want with it. There's a huge community behind ROS, so people help each other out. People write code that they share with other people, which brings to the point of sharing. But basically, the advantages of ROS makes it good for research. Because in research, you want to build robots quickly. You don't really care to make it like precise or anything like that, but you just want to build your robot quickly so you can test your ideas. So it's like good for research. You can grab libraries from here and there. You can find all sorts of things. Yeah, just it's very good for like fast prototyping. The disadvantages, though, is that ROS is still changing a lot. There's updates that come out every few years, which means that you have to change your code to make it work with the new versions, and it's kind of annoying. Recently, they have came up with ROS 2, which is like sort of completely different. Well, not completely, but there's a lot of different changes that sort of don't work with the old versions. Our team currently uses ROS 1, but at some point we will have to move to ROS 2. So some of the other disadvantages is security and reliability. ROS wasn't really designed with security and reliability in mind. So if there's like a chance that people may hack into your robot, ROS might not be the best option. Another thing is that ROS only supports Ubuntu. So if you're working with Windows or Mac OS, it'll be pretty hard to work with with ROS. And so this basically means that ROS is not really good for mission critical tasks. So, for example, if you're to send your robot into space, or if you're programming a flying robot. Yeah, if you're programming a flying robot, might not be the best idea because sometimes there can be errors that are hard to like track. Not very reliable, basically. So because of these advantages and disadvantages, ROS is like one option among many other tools. So there are other alternatives, which I'm not going to go into. But since ROS has all these advantages that we see here, we kind of prefer to just use ROS. So now we're going to go into some basics of ROS. What you see in this picture is an example of what your robot project might look like. So imagine you have a robot that has a camera and some kind of motor attached to it, say like 2 wheels or something like that. So in this case, how you could organize your code, what ROS tells you is you want to organize your code into these sets of nodes. You might imagine that maybe if you didn't use ROS, you could just write the whole thing in like one giant C++ program, have it object-oriented or something, right? But ROS says, no, don't do that. What you should do is you should break up your program into these smaller programs here. And each program does a certain task. So the whole goal of the robot is broken down into these smaller units that work together to accomplish that goal. So in our case, we have 3 programs, or in other words, they're called also nodes. So we have 3 nodes. And so we have the camera node, which is written in C++. It reads images from the camera, and then it does some processing on it, maybe some image filtering, maybe it looks for some objects in the picture. It takes that information and sends it over this link, over this topic to the planner, which may be written in Python. The planner will take this information and it will do some calculation, maybe do some kind of like path planning or whatever like that. But anyways, at the end, it comes up with some kind of motor control input, and it sends those values to the motor controller, which is written in C++. And then this motor controller will take in these values and ensure that the motors are spinning at the exact speeds the planner was asking for. So this is a sort of basic structure of what ROS program may look like. You have the nodes, which are the programs running. You have the topics, which are the things that the nodes use to communicate with each other. And you have the actual messages, which is the bits of information that actually go between each node. So yeah, that's all you need to know about the basics of ROS. This is how programs are organized. So next up, we're going to cover a little bit about URDF and Xacro. So URDF, which stands for Universal Robotic Description Format, is a file that describes the geometry and the physics of a robot. So on the right, you can see we have an example of a robotic arm, which is composed of these links and joints. So you got the three links here. The rectangles are the links, and we've got the two joints, which are the things that connect the links together. So if you think about it, any kind of robot can be represented as a set of links and joints. You can think of cars, you can think of drones, humanoid robots. I don't know. There's a lot of robots that follow this sort of configuration where you can describe them as links connected to joints. And so that's why we have this URDF file format to kind of be able to describe any type of robot. So what we can describe inside the URDF is basically these things. So as I said, the URDF can describe joints and links of the robot. It can specify the different collisions of the parts of the robot. It can specify the physics, so like mass, inertia, friction. And it can describe the actuators that are inside the joints. So it can describe like how strong the motors are, how fast they can spin, how much force they can output, and so on. So that's our URDF file. Now in practice, people don't usually use URDF because it's kind of hard to work with. You have to write a lot of like lines of code to describe a robot, and it's takes time and it's like hard. So that's why people came up with this extension to URDF called Xacro. So Xacro files are very similar to URDF, but they add on a bunch of features that makes it easy to describe your robot. And so yeah, so it just simplifies writing of your URDF files. And so our robot that we're going to be, so our robot for our team is described in Xacro. The example that I'm going to show you today is also going to be using Xacro. So we're actually working with Xacro files. So how it works actually is that the Xacro file is parsed by a program, and that in turn is compiled, sort of like compiled into URDF. Anyways, that's I think that's enough for this slide. That's all you need to know. Yeah, so this concludes the slides section, and we're gonna go into the code now. I'm currently in Ubuntu 20 with ROS Nordic installed. And before we go into our code example, I wanted to show you our robot that our team works on. So for that, I'm gonna go into the terminal. Let me increase the size a little bit. Okay. So I'm gonna go into catkin ws, and let's look around. Now, since I've already built the project, I'm just gonna launch the robot. So this is launching our Gazebo simulator, and here it is. This is Bez, our humanoid robot, looking around. We're in a soccer field. So currently the simulation is paused, but if I press space, it should unpause it. And so as you can see, the robot is now moving its head, and it's looking around. So Bez is a pretty complex robot. It has 2 motors in each of its arms. It has 2 motors in its head. It has 6 motors in each of its legs. So in total, we have 18 motors that we need to control. So it can be quite challenging to sort of wrap your head around this robot when you first start working on it. That's why we created this tutorial, so that we can introduce you to robotics with a much simpler robot, so that you can grasp the basics of ROS, basics of simulation, before you jump into our robot. Okay, so we're going to begin examining our code in our GitHub repository. So this repo, called Tutorials 2020, was prepared specifically to teach you the basics of ROS and simulation. So if you have never seen a GitHub repository before, this is the basic structure. Right in the middle here, you have the relevant files of the project. You have folders, and you have all these different files. You can click on them to have a look what's inside. You can go into the folders to explore the files. And so this is a useful way to sort of have a quick look into what's in this project, just by clicking on the files and looking inside them. So GitHub also can show you the history of files. So if you have a look, if you click on this button here with the number 16 commits, you can have a look through the history and see how people have changed the project over time. So you can see that we started this project in January 2nd, 2021. Or at least that's when we committed the first files. That's when we put the files in the repository. And then over time, people have added more things, fixes, maybe new features or something like that. And you can sort of see how the history of this project has progressed. Okay, going back to the repo. Yeah, and then there's a few buttons up here that are useful to exploring the repo further. But I'm not going to go into detail about these because this is a tutorial about ROS and simulation, not about GitHub. If you want to learn Git, that's something that you'll have to, that maybe we'll make a video about, but maybe not. But you'll learn as you go. So you don't need to worry about knowing everything right now. Just know the basics, know that Git stores history, stores the files, and that's all you need to know for now. So you'll notice that there's this nice description here. And this is basically the contents of the README file. README is here. You can click on it. It's the same content. And so the reason it's displayed here is because it's one of the most important files whenever you look into a new repository. README usually contains information about the project, background, motivation. It contains steps for building and how to use the project. So it's very important that whenever you look into a new repository, you always read the README file first. It contains a lot of important information. And so we're going to do just that, and we're going to follow the steps in this README file to, first of all, copy the project into our computer. We're going to install some dependencies. We're going to build the package, and then finally we're going to launch the robot and control it with some commands. So we're going to follow all the steps in this README file, and I'll show you how to do this so that you can do it yourself on your computer. Okay, so I have my repository on the left. I'm gonna scroll here, just a little bigger. Okay, so we're going to be following the steps in the README file. So I'm gonna open up my terminal. Make sure it's slightly bigger so you can see. For screen. Okay, so step one is we want to clone the repo. So before we clone it, we want to create this folder called cat.ws and a source folder inside it. So we're going to run this command to do so. Now before I run it, I'm going to open up this file explorer so I can see what's sort of happening as we're typing the commands in. Okay. So let's have a look. Just going to copy this, paste it, and if you notice, we just created this new folder here. So you go inside cat.ws source. Now we're going to run this command to go inside that folder. So now we're inside. And we're going to clone our repository in that folder. So I'm going to copy this and then paste it in here. And that's it. You basically copied the entire project into the source folder. All these files are exactly the same as you have seen them in our GitHub repo. They're the exact same copy, but now they're on your computer. And it was that easy. Just run one command and you get all the files copied onto your computer. Simple enough. So now that we're done cloning the repo, we're going to update our dependencies. So let's copy this. So now we're back at our catkin.ws. Back at catkin.ws. We're going to run this ROS update command. So that just updates a bunch of files on your computer. Files that point to like yeah, it updates these files here. Now, after you update those files, you want to run this command, which will actually install the needed dependencies. Before you run it, you have to make sure that your that you have the right ROS version selected. So in my case, I have ROS Noetic, so I'm going to type in Noetic here. Okay, so all my ROS steps are installed, so that's good. Next, we're going to install controllers for the robot. That's another dependency. I'll copy that and type in my password for my computer. Okay, I'm going to copy this. Now, same deal here. You want to make sure that the name of the ROS distro is matching the one that's installed on your computer. In my case, it's Noetic, so I'm going to type in Noetic here. Okay, so it's already installed, so we're good. So now, after we cloned it, after we installed the dependencies, now we can build our project. So I'm going to clear the screen. Let's copy this command here. Okay, so we're in the right folder. Now we're going to run our build command. So catkin is the tool that's used to build ROS packages. Build is just a command that tells catkin what to do. And tutorial is the package that we want to build. Now, if we have a look at our project files, we're going to tutorials 2020. There's this one file called package.xml. Now, let's have a look inside. So what this file does is it sort of describes what this package is about. Like it contains some metadata describing the package. So it has a bunch of dependencies that it declares, and then there's some more information above here. So one of the things is the name of the package. In this case, we called it tutorial. So because we called it tutorial, whenever we want to build this package, we have to mention the name tutorial. So that's where the name is coming from, and that's what I wanted to point out. But I guess let's have a look at the other stuff here. So you've got version, got this description of the package, which tells you what the package contains. So in this case, it says the tutorial package contains example robot. There's the email address of the person who maintains this package. In this case, just some random email, my name, license, and then there's the dependencies, as I said before. So that's what makes up a package.xml file. Okay, anyways, I'm gonna press enter, and that's gonna build our project. Okay, so all 2 packages succeeded, so we're good. So after we build our package, an important step is to run this source command. It's important because it tells your computer where the build files are. If you didn't run this, then you wouldn't be able to run the next commands that are following up. So I'm just gonna paste it in, and we should be good. So I'm just gonna clear the screen now, and we're ready to launch our robot. So I'm gonna copy this. ROS launch is just a tool for launching special files. Tutorial is the name of our package, as I mentioned before, and gazebo.launch is the file that we want to launch. Okay, so let me go ahead here. And okay, this is our example robot that we're going to be working with. As you can see, it's a simplified version of our humanoid robot. It has only 4 different parts to it. It has the 2 arms, the head, and the body. So it's going to be a really good example for you to get started with ROS, learn the basics of how you can create this kind of robot yourself, and how you can write code to control this robot. So what we're going to do is we're going to have a closer look at the code that generated this robot. I'll walk you through all the code. I'll explain to you everything so that you understand how this works. Before we do that though, I'll just show you how you can control this robot through command line. So I'm gonna pull up my command line. Okay, and we're gonna type in this this command, ROS topic pub, and we're gonna put in the topic name. In our case, we want to send it to left arm command. So what I did here is I pressed tab, and this auto completes my my name here because it already knows what I'm trying to type in, so it just finishes the rest of it. So this is a useful tool whenever you're working with command line. Just press tab to complete your commands. So I'm going to continue to press tab to continue to fill in the rest of the command. So there you go. That's a full command. And I'm going to tell it to go at 1 radians per second. So what this should do is it should spin the left arm at 1 radians per second. So let's see what happens. Yeah, and there you go. The arm is spinning and the robot is thrashing about on the ground. Now, if you want to stop it, I'm just going to quit this program. If you want to stop it, then you want to run, you want to send a 0 command. So this would tell the arm to stop. So let's send it. And as you can see, the robot has stopped moving. So in this way, you can send simple commands to the robot to move its arms. I could do the same with the right arm. So instead of sending it to the left arm controller, I'm going to send it to the right arm controller. Okay. So right arm controller. What is going on here? Send it a 1. Oh, okay. Float. Okay, send it a 1 or 0.01. Okay, I think there's some misspellings. Okay, I'm just gonna clear the screen. Just type the message from the beginning. So the ROS topic pub right arm. Press tab to complete it. Press tab again. Tab. Give it a 1, and then we'll see it move. So now the right arm is moving. Again, if you want to stop the arm, you just have to send this exact same message, but this time you just send a 0 to tell it to stop. So we'll send a 0. And it stops. Okay, now kill this program, clear the screen, and go back to Gazebo. Now if you press Control R, this will reset the robot. So Control R, and our robot is back. You can also control the position of the head by sending this following command. I'll stop it. Tab, head, controller, tab again, tab again. Now the head takes in a position value in radians. So for example, I can tell it to turn -1 radians. And then that turns the head in the negative direction. Now if I send the message again, but this time make it positive, it'll spin in the positive direction by 1 radian. So yeah, this is a way for you to control the robot through command line. And all these commands I have added them into our README file. They're all here. There's examples of how to send a command to the arm. There's also commands for other things. So you can always check the README file to see how to do this. Okay, but now we're gonna go explore the files of the robot and see how this is done. Okay, let's have a look at the files. So I'm gonna go into cat WS source. I'm gonna go inside our package, and let's start exploring the files. So I've already mentioned README file, which we have seen on the GitHub page. We have looked inside the package.xml file before. CMake list, let's have a quick look. This is basically a file that defines how you have to build the project, or how the tool will build the project. You don't have to worry too much about this. Just know that this is used whenever you want to build your C++ files, or you want to build some other type of files that needs building. Then we have these 4 folders. So I want to start with, let's see, let's start with launch. I think this is what we've interacted with a few times. So if you look, if you remember, gazebo.launch is the file that we launched on our command line to start up the simulation. So the structure is this. It's a basic XML file format. You have tags, and you have arguments inside those tags. So just like the format of the code. So what the launch file is, it's basically sort of like a script file that helps you run multiple commands at the same time. Instead of typing these commands into the terminal, which takes some time because you have to like type in stuff, you have to press tab and stuff, you can just write those commands in this file. So I'll quickly go over the file, just give you an overview of what's happening here. So argument, so we're defining, here we're defining the path to our Xacro files, which are the files that describe how our robot looks like. So we're saying these files are located in this folder, and we save that into this variable called model. Over here, we parse our model files, we parse those files, and we save it into a global variable called robot description. This will be used later on to spawn the robot in our simulation. So after we do the parsing, we run this script, which starts up our Gazebo simulator. We pass in a few arguments in here. We're not debugging. We want the GUI to be turned on. We want the simulation to start paused, or actually not unpaused, so it starts right away. And a few more arguments. So this starts up the simulation, and then here we have a command that spawns our robot. And so you'll notice that we pass in some arguments here. One of the arguments is this robot description, which we have defined over here, robot description. So we're passing in robot description so that this node can spawn a robot in simulation. So once the robot is in simulation, like we can see the physical robot, we run this command. And this command just loads in a few configuration files. In this case, we load, I'll go back to our files. We load a bunch of variables from this file here. And these variables are just defining the different controllers for our joints. So for example, we have the head controller, which is position-based controller. We have the right arm controller, which is a velocity controller. Left arm controller, which is also a velocity controller. So this line over here just loads these values into the global parameters. And then those values are then used in this next node, which spawns these controllers. So we need to spawn these controllers in order for us to be able to send commands and control them in simulation. So yeah, that's the basic structure of our Gazebo launch file. There's quite a bit of going on in here, but just understand the basic high-level view of what's going on. We're just loading our robot, we're starting the simulation, we're spawning our robot, and then we're loading a bunch of controllers so that we can control the robot. That's basically what we're doing here. So now we're so close these. Now let's have a look at the simulation files. So I'm gonna go back, and we're gonna go into the URDF folder. So here you can see we have a bunch of files. The important ones are the Xacro files, which define how our robot looks like. So we're going to begin by looking at main.xacro. Okay, so this is main.xacro, and again, this is also a XML type file. So we define the robot using these tags, links, and other types of tags. So we start off by defining the robot tag, where we specify the name of our robot. In this case, I called it my robot, but you can call it whatever you want, but you have to be consistent with the robot name throughout the different files. So looking through, we have some include statements. We're including these two files. We're including arm.xacro and head.xacro, which are these two files here, arm and head. And then we have our first element in our robot, which is the first link. We call it base link because that's sort of the convention in ROS, or in ROS, to call the first link of the robot the base link. And in our case, the base link is just the body of the robot. So we can see that there's 3 tags inside. We define the visual of the robot, of the link, the collision of the link, and the inertial properties of the link. So inside the visual, you can see that we've defined it to be a box of size of 1 by 1 by 1. So basically a cube. In collision, we define it to be the same, 1 by 1 by 1, a box. And usually you want the visual link, the visual tag and the collision tags to have the same values, usually, when you're working with like simple shapes. In the inertial tag, we specify how heavy this body is and what are the like rotational properties of it. So these values are important if you want your simulation to be accurate in terms of like it matching like real life, how it like react in real life with the physics. Yeah, so we define our body here. That's the link, and then here we define the other links. So we define the two arms. But the right arm, we say that it's 0.7 units long, 0.2 units in radius, and the reflect just says on which side of the robot it is, 1 being right, -1 being left. And then finally, we define the head of the robot, and in the end here we have the Gazebo tag, which includes this Gazebo ROS control plugin, which is needed to control our robot. Not too important for you to know, but it's just there to make our robot work. Yeah, so let's see what happens if we change some of these values. So if I go in here and I change the value of this to be 2, and again, I'll just make sure that the two values here are matching. So I'm changing both to 2. Okay, I'm gonna save the file, and what we can do is we can, I'm just gonna clear this. What we can do is we can launch this this new file. So the thing is, we don't have to build anything. We can just launch the file right away. So I'm going to ROS launch tutorial. No, not turtle. Tutorial, and then gazebo.launch. And let's see what happens. So as you can see, the body just became 2 times longer. So instead of being a cube, now it's a 1 by 1 by 2 rectangle, I guess, or prism or something. But yeah, so you can see that it's really easy to play around with this. You just change the value, you launch the file, and then you can just see the results. Okay, just gonna build this now, and then I'll change this back to 1. Okay, so we went through the main.xacro file. Now let's have a look at the arm.xacro files. So I'm gonna open up this. So I'll close this. So okay, we've got a little bit more going on in here, but it's not too bad. So let's step through line by line. So we open up with the .xml tag. Then we specify this is a robot file. Again, we make sure that the name of the robot is the same as the name of the robot in the other files. And then we specify the type of I guess file this is. In this case, we call this file arm. And we specify the parameters that you can pass into this file. So again, we have a link. This link describes the properties of the arm of the robot. You can see that we have a visual tag, we have a collision tag, and we have the inertial tag. In the visual tag, we see that there's a new thing here. We have the origin of this link, and actually this appears in every one of these tags. So you have origins appearing in all of these tags. I'll get into origins a bit later, but notice that in geometry we defined a cylinder instead of a box. So you remember the robot had cylindrical arms, and we defined the length to be whatever the user has passed in, the length, and the radius to be whatever the user has passed in as the radius. So the link describes the arm, and now we have the joint tag, which we haven't seen before. And basically what the joint tag does is it defines how two links are connected. In our case, we specified the two links to be the base link, which is the body of the robot, and this prefix arm link. In this case, the prefix will be replaced by left or right. So it could be left arm or right arm. But we define the link between these two. We define the connection between these two links. And so the way we define the positions of the two links is through this origin tag, which we saw before. This origin tag has two arguments. It has the RPY and it has the XYZ. So the RPY is stands for roll, pitch, yaw, and it basically describes how the link is oriented with respect to the other link. XYZ is what you'd expect it to be. It's just defining the linear translation of the two links. So, for example, in our case here, we're saying that the arm is 0.7 units away from its body, and then it's also rotated by 0.2 radians away from the body. So let me just run the simulation so you can sort of see what's going on. Okay, I put it off to the side, and let's make this kind of transparent. So let's have a look at the skeleton. So you can see it's transparent. When I look at the link frames. Okay. And we want to look at the joints. All right. So going back to this joint example, what you can see is that we're defining the connection between the base link and the arm link. So the base link is over here, this coordinate here, and the arm link is over here. So what we're doing is we're saying, okay, the arm link is 0.7 units away, so it's 0.7 units away on the y-axis, which is the green axis here. And we're saying that it's rotated by 0.2 radians. So normally this would point up straight, but you can see that the arms are a little bit slanted to the left, right? So the 0.2 is what's causing it to be slanted to the left. Another thing I want to point out is this axis. This axis tag, which defines where is our axis of rotation. In this case, we defined the axis of rotation to be the y-axis. We put a 1 here, to say that the y-axis is our axis of rotation. And if you look at the simulation, you can see that there's a yellow circle around our green axis, which is the y-axis. So this says that the arm will rotate about this green axis here. So this is basically what the origin and the axis tag do inside this joint tag. Now you may ask, then what's the point of this origin tag in our link? Why do we have 3 of these? And that's a good question. It's a bit confusing because it doesn't really make. It's kind of weird that we have 2 origins here to specify where our arm is. But to try to simply explain it, well, first of all, this is we need these tags to fully describe the robot. So it's like necessary. It's not like someone added these tags because why not? But these are actually important and needed to fully describe the robot. But the way it works is that the joint origin. So the joint origin describes where the next link is. Okay, so it tells us that our next link is over here. Now, what these origins do is they describe the various parts of the link. So in this case, we want to. So for example, let's focus on the visual. We want to describe where our visual part is with respect to our joint. So in this case, we're saying we want our visual part, the cylinder, to be 1 unit up in the Z direction. So you have a look here. What we can see is that the cylinder is, you can see that it's offset from the origin here. It's offset by 1 unit. It's 1 unit up. Now, to give you a simple demonstration, let's see what happens if I change this value to be 0. Okay. So usually when you change these values, you want to make sure that they're all the same. This is true most of the times. There are special cases when that may not be true, but those are rare. It won't happen if you design your route properly. So usually these 3 origins should have the same values. Anyways, I'm gonna set it to 0 and let's see what happens to our robot. So I'm just gonna kill this simulation. Okay, I'm gonna rerun it. So as you can see, the arm suddenly dropped down by 1 unit. So let's have a look again at our skeleton. Let's look at our links. Look at our joints. So as you can see, the arm just dropped down by 1 unit, and now it's centered about this joint. So hopefully this kind of shows you what this origin does. I know it can be kind of confusing to kind of wrap your head around why there's like origin here, why there is origin there. And I get it because it took me a while to wrap my head around this. It's kind of confusing with all the 3D like links, joints, all these reference frames. It's pretty hard to like grasp it on the first try. So my advice here is just play around with this file, change the values, see what happens, and try to just get an intuitive sense of what's going on. Don't worry about like understanding it like right away. It takes time. Just continue to like play around and learn. All right, so we covered the ARM files. Next up, I want to quickly cover the head file. So let's have a look at the head. Okay, so if you look inside the head file, what you'll notice is that it's actually very similar to our ARM file. I'm just like switching back and forth between the two. You can see that they're pretty similar, right? Similar structure. In the head file, the difference is, well, let's mention the similarities. The similarity is that we have a link which defines the head, like the blob of the head. So we've got the visual, what it looks like, the collision, how it interacts with collisions, and inertial is how it interacts with the physics of the world. We have a joint, which defines how the head is connected to the body, as before. Transmission, I think I mentioned transmission before, but transmission is basically defining a motor interface inside of our joint. This is what allows us to basically move the joint. Not important for you to know, just know that this is basically the motor of the joint. The more important parts are the links and the joints. But very similar structure as to the arm. The difference is that instead of defining a simple shape, we're defining a mesh file. In this case, we use this head.dae file, which you can see in our folder, head.dae. And this is basically a CADing file that you get when you design your thing in a CAD software. So if you're wondering how we go from the design of the robot into simulation, this is what happens. Our mechanical team designs the files in Fusion 360. Then they will export those files into .dae or .stl files. And then we, the software team, we take those files and we put them in here, in our Xacro files. And finally, they appear in our simulation as these nicely rendered objects. Now I've included this additional file called shrek.stl. So this is sort of for fun. I went on Thingiverse and I downloaded a model of Shrek's head. So to demonstrate you, I will kill this simulation. And in here, I'm just gonna type in shrek.stl. Okay, and I will make sure that it's slightly smaller. Okay, shrek.stl. Now let's run our program and see what happens. So at first when I did this, I thought that you know, maybe there was some kind of bug because nothing was appearing around the body. But then when I had a closer look and I looked around, it turned out that in fact it was working, except that the head model was really, really big. Yeah, so this is one of the things you have to be like careful about when working with STL files, is where is their origin defined. In this case, the origin was defined way off the center of the head, and so that's why it appears all the way out there, and also the scaling is kind of wrong. So we have to fix that too. But yeah, well, this shows you that working with STL files can be a bit tricky, but also it shows you that you can easily import your own files. So if you have your own CAD files, if you download files from internet, you can easily add them into your simulation just by basically typing in the name of the file. It's easy as that. All right. So we've covered URDF files. We covered Gazebo launch file. I think what's left is to look into writing our own node files to our own C++ files to control the robot. Okay, so now let's write our C++ file. So we're going to go into our source folder, and we're going to modify our main.cpp. So currently, our main.cpp contains a simple hello world. We're going to expand on this to add in all the different ROS libraries, calls, and functions so that we can communicate with our robot. So for now, the first step is, before we do all of that, we need to first build this project and be able to run it. So let's do that. Now, before you can build the project, the first step is you need to make sure that your file is included in our cmakelist.txt. So let's open up cmakelist.txt. And if we have a look at the last two lines, I have already done that. So we have this line, which adds our file and gives it a name. So in this case, I call it my publisher. And then we link some libraries. In this case, we're linking the ROS libraries into my publisher. So if you want to build your C++ files, you have to make sure that you have these two lines included in your CMake list. Okay, so once that's done, we should be able to build our project. So if we go back to our terminal, we are inside catcon.ws. I do ls, you can see that we have the build, devel, logs, and source folders. So here we're going to run our catcon build and then tutorial, which is our package. We press enter, and our package built without any problems. So after we build it, remember to always source your project. So it's devel setup.bash, and then we should be ready to go. So to run your program, or to run your node, what you want to type is this: ROS run your package name, in this case tutorial, and the name of your node. In this case, we call it my publisher. So if I run this, we get a hello world, and yeah, so that's how you build and run your node. Now, as a next step, we're going to modify this to include the ROS functions so that we can communicate with our robots. So In order to do that, I'm going to refer to some tutorial, which was not written by me. There's a link here. I click on it. We go to our official ROS.org site, which has various tutorials. The tutorial I'm interested in is writing a simple publisher and subscriber in C++. So the thing is, I don't remember how to exactly write the programs. Like there's a lot of things you have to like memorize, which no one will remember, right? So I'm just going to refer to this tutorial to kind of remind me what I need to do. So the tutorial gives you just straight up gives you this whole code on how to set up the publisher, subscriber, and how to send things to your into a topic. And it also goes line by line to explain what each line of code does. So it can be useful when you're starting out to learn from these tutorials. Okay, so what I'm interested in is not a subscriber node, but I'm interested in the in this publisher node because we want to publish a message to our robot. So what I'm going to do is I'm going to put this on the other side. So we have our code in here and we have our code. We have our code and we have their code. That's what I meant to say. Okay, so first things is I need to include ROS. So let's do that. So I'll do it here. Include. Okay. Okay, so they're including this string.h, but since I already know that our robot takes in a float 64, I'm just gonna include our patch for the float 64. So it's std messages float 64. Okay, so we have done that. So step one is we need to initialize our ROS. So I'm just going to do that. I'm also going to add a new line here. Okay, so ROS init, pass in the argc, or passing in the argv, and we want to give it a name. So I'm just going to call it my little node. My little node, why not? Okay. Okay, that's fixed up. And next step is we want to have this ROS node.n. So maybe I'll just copy it straight. Let's save myself some typing. Okay, so the node handle is just a way for you to access the different ROS functions. So that's why you need to include this. In our case, we want to define a publisher. So I'm just going to copy this line over here. So defining a publisher, in our case, let's call it arm pub. So we do advertise, std messages. We're using a float 64. And then we have to include the topic name, and we need to include the number of messages that we want to buffer. Don't worry too much about this for now, but that's something that you'll might need to know later on. But for now, it's not too important, so I'm just going to skip over it. But now we have to put in our topic name. So how do we know what's the topic name for controlling our arm? So one way of doing this is we can simply just run our simulation. So I'm going to do that ROS launch tutorial, which is our package, gazebo.launch. Okay, so here's our robot. Just gonna minimize this for now. Open up a new terminal. Make it slightly bigger. There we go. Okay. And what we can do is we can list all the available topics that are currently in ROS, in this like instance of ROS running. So to do that, we're gonna use the ROS topic tool. So I'm gonna do ROS topic list. And what that does is it lists for us all the available topics that are currently available in this instance. So if we look down the list, we can see that there's these topics that are exactly what we want to control. So we're just gonna copy this name, copy it, and we're gonna paste it in here. So now what we have done is we have defined a publisher that publishes to this topic, left arm controller command. And so now what's left to do is we need to make it actually publish values for us. So in this case, let's have a look. So in this case, we're having a while loop, and we're constantly sending data. So let's do that. So I'm going to do a while. In their example, they use while ROS is okay, which is fine. So ROS is okay. So while is ROS okay, then just keep going, keep doing stuff. So what I want to do here for this example is I want to take in the user input. Let's do something like char in. Okay. And we're going to do std cin. We're going to put the input into our char variable. Okay, so what's going to happen is the program is going to go into this loop, and it's going to pause here and wait for our input. So for now, we're not going to do anything with the input, but what we're going to do is we're going to send a simple value. So first we need to define our message. So if we have a look here, where is our message? So they define a standard string message, okay? So we're going to do the same thing. Standard messages. We're defining a float 64. Let's call it speed. And we're going to let's call it speed message, just to be clear. So speed message dot data, we're going to set it to 1.0. And once that's set, we're going to publish this message. So what we're going to do is we're going to call our ARM publisher. And we're going to say ARM publisher.publish. And in our case, we publish our speed message. And that is all there is to it. I missed a .h in here. But it seems fine. Okay, so we have our program. Let's try to build it and see whether it works. So we're going to do captain build tutorial. Okay, never mind. So we got an error. Okay, that's fine. Let's just make this a little bigger and let's see what's happening here. Okay. So error float 64 was not declared in the scope. Did you mean standard messages float 64? Float 64, STD messages. Okay, I think I see the problem here. The problem is I forgot a colon. All right, let's try building this again. Okay, more errors. Our speed messages was not declared in the scope. Did you mean speed messages? Messages. Yes. I didn't mean speed message. Okay, so small typo. Let's try building it again. Okay, so our program built. Now let's try to actually run it. Okay, let's pull up our simulation. I'm gonna put it off to the side. Okay, and let's see whether our arm moves. Okay, so here I'm just gonna clear the screen and we're gonna type in our command. So we're gonna do ROS run and then our package name and our node or the program that we wrote. So in this case, we called it my publisher, right? Okay, so if I press enter, all right, so nothing is happening. Okay, well, let's try to debug this. Let's see what the issue is here. Left arm controller command. It's weird that it's not. Something weird is going on here. Okay, I'm just gonna kill this for now. So from what it looks to me, this should be okay. Left arm controller command. Okay, I'm just gonna launch our simulation again. See if I can figure out this issue here. So put this off to the side. We have our robot here. We're going to increase the size a little bit. Okay, so let's do ROS topic list. Let's look at our available topics. Left arm controller command. That's right. Okay. We have main. Left arm controller command. Publisher. publishing this, ARM publisher, cden. Oh, okay. Okay, I'm kind of silly. I forgot that we take an input before we do anything. So right, so I think our program should work actually. It's just that I forgot to enter a value here. So let's make this more explicit. Let's do std cout, please enter a value. Okay, yeah, I think it should work actually. Okay, so I'm just gonna save that. Let's build it. Catkin build tutorial. Tutorial, please. Okay, so we got that's working. Clear the screen. We're gonna do ROS run tutorial and then our file name, which in this case is my publisher. Okay, there we go. So now it's asking please enter a value, and we are right here waiting for input. Okay, so last time I just forgot to press enter, which is kind of silly of me. Okay, so let's see what happens. Let's enter a random value, say like A. And there you go. Our arm is rotating. So yeah, that's as simple as that. You just have this program controlling your robot now, instead of you typing the commands in the terminal. Okay, so let's, how do I stop this program? I feel like I have to press Control-Shift-C maybe. Control-Alt-C. Control-D. Yes, Control-D. Okay. So let's improve our program a little bit so we can have more control over the robot. So as an example, we could take this input now and we can put it in a switch statement. Okay, input in switch. Here we should actually define this outside here, and we could have case if we press A, then set the speed to 1. If the case is, I don't know, let's say S, don't forget to add your breakpoints, break statements actually. If it's S, then we set it to 0, and if it's D, we'll set it to be -1. Okay. So now we build this. Let's do build tutorial. Okay, and then if we run it, so first clear the screen. I'm going to do ROS run tutorial. The name of this node, just my publisher. Okay, so print hello world, please enter a value. Okay, so ASD, okay. So if we type in A, it still spins as it was spinning before. If we type in S, it will stop. If we type in D, it will spin in the other direction. So there you have it. You've got a simple program that can control your robot. And in a similar way, you can imagine how you could add another publisher to control your other arm. Or you can add another publisher to control the position of your head. And let me do that just for fun. So I'm just going to copy this, put it in here. So this time we want to use right arm controller. And we're going to call it, so we're going to call this left pub, and we'll call this right pub, okay? So in this case, left pub. And let's just send the same message to the two different, to the two arms. Okay, so we're publishing to left arm and we're publishing to the right arm. Okay, so I'm gonna kill this program. Oh God, okay. Let's clear that. I'm gonna build it, so I'm gonna do catkin build tutorial. Okay, and then gonna run our program. So ROS run tutorial my publisher. And then let's have a look at what's going to happen. So if I press A, we have that the two arms are spinning now. If I press S, the arms stop. If I press D, the arms spin in the opposite direction. Okay, there you have it. This is our simple program for controlling our robot. Okay, so this leads us to the end of our tutorial, and I want to leave you with this exercise. So I want you to take the current repository, and I want you to do some modifications to it. So number one is I want you to modify the current Xacro files to make a wheeled robot. So currently the robot looks sort of like a humanoid, but I want you to make it look something like this robot on the right. It should have wheels that touch the ground, and it should be able to move around. So then number two is I want you to modify the C++ program in such a way that you can control your robot movement. So I want you to be able to tell your robot to go forward, backwards. Your robot should be able to turn on the spot, and you should be able to control the speed of the robot. So as you do this exercise, you should be able to learn more about ROS, about Xacro, URDF, about Gazebo simulation, and that should give you a lot of experience, initial experience when working with ROS. So yeah, so I hope that you learned a lot from this tutorial. Took quite a bit of time to prepare all of this. So yeah, so I hope that it was good. If you have any comments, suggestions, I guess write them below or whatever, or contact the leads and tell them what to improve, what not to improve. But yeah, hope you found this useful.